Welcome to our presentation on the detection of PFAS chemicals in a water sample.
What are PFAS chemicals? So, PFAS is an abbreviation of per and polyfluoroalkyl substances. They are highly fluorinated aliphatic substance, and they have a terminal functional group such as carboxylic group or SO3H. Some examples are PFOA and PFAS. So PFOA is perfluorooctanoic acid and PFAS is perfluorooctane sulfonic acid. Now, these chemicals are of interest because the CF bond is one of the strongest bonds, and these chemicals have an extremely long half-life and are not usually broken down or can't be broken down in biological systems. They can also be branched, but this is less common. Uses and applications are they're in non-stick coatings, or they were in non-stick coatings. They are stain resistant, and they were seen in industries such as aerospace, automotive, construction, electronics, and military. They are also resistant to heat, oil, and water, which is why they were seen as very useful. However, they are no longer used much as the toxicity is now being recognized. If you want to see more information on these, you can look at the link here and the reference here.
This slide is on the dangers of PFAS in water. These chemicals are known to have a range of health effects, including cancer, immune system dysfunction, liver damage, developmental and reproductive harm, and hormone dysfunction. These health effects are the reason why it's so important to be able to analyze water for PFAS.
Analytical techniques used to detect PFAS chemicals in water. So the first one is HPLC, that's high performance liquid chromatography. And here's some brief information about them here. High operational pressure, it's got a non-polar stationary phase, and a UV vis detector is used for the samples produced to analyze them. UPLC is ultra high performance liquid chromatography, has a much higher operational pressure than HPLC. It's got very small column particle size and a much higher resolution. The third one is GCMS, also known as gas chromatography mass spectrometry. So the sample is vaporized when it first goes in. The propellant for the sample would be inert, and it can do a full scan of the sample, or it can do selected ion monitoring. The fourth one is LCMS, so that's liquid chromatography mass spectrometry. The liquid chromatography occurs in a pressurized liquid, just like HPLC and UPLC. The eluent is vaporized before the ionization, but after the chromatography, and it is mostly used for larger molecules. The final technique is SPE, or solid phase extraction, is used to isolate analytes of interest from a sample or concentrate them more. It occurs under vacuum, and it can occur in normal or reverse phase.
This slide is on how HPLC and UPLC detects PFAS chemicals in a water sample. HPLC and UPLC work in similar ways, that's why I only have one schematic for both of them. Two solvents are used. One is water, and the other one is usually methanol or acetonitrile. A pump is used to create the mobile phase. It sucks up the solvent, pushes it along. Then the sample is then injected into this mobile phase. It goes along to the column, where it enters the stationary phase inside the column, inside the reverse phase column. Sample then separates and then leaves the column and is detected by the UV vis detector, which sends a signal to the computer to display a chromatogram, and you'll be able to analyze this and see if there's any PFAS in the water. The sample and solvent then just continue on to waste. There's differences between HPLC and UPLC. Mainly, UPLC is much more efficient than HPLC. It takes much less time, uses much less solvent and the sample. This could be useful if you only have a small amount of the sample. UPLC also produces higher resolution data. This happens because UPLC is a much higher pressure compared of greater than 1,000 bar compared to HPLC with only a pressure of 50 to 350 bar. UPLC also has a smaller column particle size in here.
How LCMS and GCMS detect PFAS chemicals in water samples? So GCMS, it has a very small sample size, so when you would complete an analysis, you would inject a very small sample, micrograms, into the machine. It would be vaporized in the heated zone, and this heated zone can vary in temperature to get the best separation of the analytes. Then a carrier gas, which would be inert, which could be helium or nitrogen, carries the sample to the stationary phase, and it passes over the stationary phase. The retention time is recorded over the stationary phase, and then the eluents are ionized and a mass spec is completed on that, and the MZ ratio is recorded and compared with the mass spec library. So this is a Perkin-Elmer GCMS machine here. So this large bit here would be the oven, which is where the vaporized sample is in a heated zone and the temperature can change in here to get the best separation. The next one is LCMS. So it has reverse phase for the chromatography part, and it's got very similar conditions to HPLC or UPLC. The mobile phase is polar, and the stationary phase, is non-polar. It's got very small sample size, so when you inject a sample, you only need some microliters of it. Once again, the retention time is recorded, and this can be compared with standards that would have been analysed in the same matrix. Then before the mass spectrometry is completed, the pressure needs to be reduced, and then the liquid sample needs to be vaporized after it's been through the UV vis machine. Once it's been vaporized and then ionized, the MZ ratio can be recorded and compared again with the MZ library. So here is a picture of a Perkin-Elmer LCMS setup. So here you can see the chromatography machine on the desk. It looks a bit like a HPLC machine. And then on the left, you've got the mass spec where the sample would come out and go into that machine. Some limitations of GCMS are mainly with the mass spec side, because the PFAS chemicals have very low fragmentation, and that's partly due to the CF bond being so strong. The water matrix can also pose a challenge, as this can hinder accurate MS detection and analysis of the sample.
This slide is on how solid phase extraction, or SPE, detects PFAS chemicals in a water sample. SPE is a very common method of extracting PFAS from aqueous solutions, and methanol is used as the eluent. SPE extracts and cleans the PFAS, then allowing it to be analyzed by LCMS. SPE takes lots of time to do and also uses lots of the sample to acquire enough to be analyzed. But before you add any of your solution to the cartridge, you have to prime it with methanol, and that enters the silica that's in the stationary phase. You can then add your aqueous solution, so that's that there, the PFAS and the other impurities. Now this is under pressure, so methanol is then washed. Methanol is then used to wash away any of the other non-PFAS impurities, leaving just PFAS and methanol in the cartridge. So then PFAS is then extracted out using 0.5 ammonia methanol solution. Cartridge is then dried out with nitrogen to be reused again.
So how did these techniques help with the problem? So all these analytical techniques can be used for large-scale sampling, and so multiple samples can be taken from many locations, and then this can be used to map areas or nations with poor drinking water and can also highlight areas with good drinking water. So a common area where they have this issue is the United States, and as you can see here, there's a map. This map highlights areas with high PFAS concentrations, and obviously the areas where there aren't dots is low concentration or none. So this link highlights an interactive map, which is the same as this one. So after this analysis, the resources could be redirected. So fresh clean drinking water could be brought in, or the water systems that are used currently could be updated or improved to enable cleaner drinking water. This could also highlight improper industrial practice with regards to waste material, as they may be putting waste material in landfill and then the PFAS chemicals may be leaching into the water table and then into drinking water systems. This data could also be used in correlation with some health issues and as to why they're on the rise in some areas and are less prevalent in other areas. Thank you very much for watching our presentation.